In this example, we will look at buckling of a plate. The plate is pinned at the base and pinned at the top. The supports at the top allow for vertical translation. The plate is loaded by a distributed load W, and the plate has dimensions B, H, and T, where the width of the plate, B, is 10 inches, the height of the plate, H, is 50 inches, and the thickness of the plate is 1 inch. The plate is made of steel, and it has Young's modulus equal to 30,000 KSI. And the plate is also made of a grade of steel that has a yield strength of 50 KSI. We will model the plate first, assuming linear elasticity, and then we will account for yielding by modeling the stress-strain relationship using a Ramberg-Osgood model. If you look in the literature on the Ramberg-Osgood model, basically it's a nonlinear relationship between stress and strain, and the equation is shown on the picture here. In the equation, E naught is Young's modulus, and sigma naught is the yield strength of the material. The parameters A and N are typically chosen so that the model fits the experimental data, and so we will use A is equal to 0.002 and N is equal to 5, just based on some values that I found in the literature for steel. As I mentioned, we will model this problem first, assuming linear elasticity. And this is a pretty simple problem, so we can actually calculate the critical load just using the Euler buckling formula. So P critical for a pin-to-pin plate is going to be pi squared EI over L squared. And if we plug in the values for this particular problem, we find that the critical load is 98.7 kips. The load is not applied as a point load in this problem, it's applied as the distributed load. And so to figure out what W critical is, we would take that 98.7 kips and divide it by the width of the plate. And that gives us 9.87 kips per inch. So as I mentioned, we're going to use a couple of different modeling techniques, first assuming linear elasticity, and then later we will introduce the nonlinear material behavior. We're going to do all of the modeling in Abaqus, and so what I'm going to do now is switch over to Abaqus so that you can follow along. The first thing we're going to do is we're going to create the geometry. So we're going to double click on parts. And the modeling space that we're going to be using is a three-dimensional modeling space. The base feature is going to be shell, and we can do this either as a planar sketch of the rectangle of the cross-section, or we could do it as an extrusion if we just extruded a line. Both should give us the same answer. If we do the planar, what I'm going to do is I'm going to draw a rectangle that is 10 inches wide and 50 inches tall. And then we click done. And so there's our part. One thing I'm going to do is I'm going to partition the part so that we will have nodes that are exactly at the mid height. Okay, so I'm going to go to this option, partition face, sketch, and I'm going to, let's see, select your axis that will appear vertical and on the right, be this edge here, and I'm just drawing this at the mid height here, and then clicking done. The next thing we need to do is we need to create our material. We're going to create two materials. One is going to be linear elastic. So I'll call this one steel linear elastic, where it has elastic properties. Basically, we just need to give Young's modulus and Poisson's ratio. And for Poisson's ratio, let's use 0.3. And we'll click OK. Let's also create the material for the Ramberg-Osgood model. And we'll call this steel nonlinear. And this is a plasticity model. And let me see if I can find it here. It's referred to as deformation plasticity. And we have to enter Young's modulus, Poisson's ratio, the yield stress, which was 50 ksi, exponent, which is the n constant, which is 5, and then the yield offset is what we have for A, and we'll put 0.002 in for that. Okay, so that's our Ramberg-Osgood model. And if you weren't sure what these different values were, you could go to the Abaqus help manual and it'll explain more about what you're supposed to put in for the exponent and for yield offset. Okay, so we have our two materials here, but we're going to start with just using the linear elastic properties. So what I need to do is I need to create a section. This is going to be a shell section. And I'm going to call this plate linear elastic. The type of section is homogeneous. It's just made of one material. We click continue. And for the shell thickness, this is where we can enter that the thickness of the plate is going to be 1 inch. And for the material, we're going to choose steel linear elastic. And then we don't need to change anything with regards to the integration rule. So we'll keep the default. Then I need to assign the section to the part by clicking on Section Assignments. And I'm holding in on the Shift key as I select both regions of the model. And I'm going to click Done. And we don't really need to change anything here. Basically, it's saying that our section assignment is the linear elastic plate. And the shell offset is the middle surface. What this means is that this geometry that I've drawn here is at the mid depth of the plate. It's not at the top, it's not at the bottom. And now the model has turned blue, so everything's good to go. The next thing we need to do is we need to create an assembly. And basically I need to create an instance of the part, and I'll click OK. And so now we have our plate, and it's just kind of floating here in space. Let's apply the boundary conditions. And we'll do this in the initial time step. The boundary condition at the bottom is a displacement rotation boundary condition. And we're basically going to select this edge down here at the bottom, and we will restrain it in the U1, U2, and U3 directions. I'll create a second boundary condition, and this one will be for the top of the plate. And we will restrain it in the U1 and U3 direction, but we will allow it to move in the U2 direction, or in other words, we're going to allow vertical translation in this plate. So we're going to click OK. Now coming back to the steps. The first type of step we're going to use is we're going to do an eigenvalue analysis. The eigenvalue analysis is useful for just figuring out what the linear buckling loads and mode shapes are for a given structure. And so to do that, we double click on steps. I'm going to call this step eigenvalue. And the procedure type is a linear perturbation. And specifically, what we want is we want to do a buckling analysis. So we choose buckle, but you can see that you can also get do a vibration analysis, to get the natural frequency or those kinds of things. But yeah, we just need to do a buckling analysis. So we click OK. And in this, we're going to stick with the standard solver. This is an important thing. So the number of eigenvalues requested. So let's say you just want the first 3 modes, then you should specify that here. If you don't provide a number there, then what they will do is they will give you as many modes as you have degrees of freedom. And so if you have a big model, then you might be getting a lot of information and not all of it is of interest to you. And I think everything else looks fine, so let's go ahead and click OK. Now what I need to do is I need to apply loads. And so I need to apply that distributed load along the top edge. And I believe we will do this as a shell edge load. We'll select that top edge, and we could choose any magnitude. Now, we're not told what the load is in this problem. Our goal is to figure out what the critical load is for buckling of the plate. We did some hand calculations, and we found that the magnitude of that distributed load was about 9.87 kips per inch. But if it were a more complicated structure, we wouldn't know that ahead of time. So we're just going to give it a magnitude of 1. And I may need to change this depending on which direction the arrows show up, so just bear with me. And we will go ahead and click OK. Let me zoom out here. Well, let me just pan. So you can see that the load is in compression, so that all looks okay to me. Okay, so I think we are all set. We just need to create a mesh. And for this mesh, I'm going to assign mesh controls so that I have a uniform mesh. So I want to use structured meshing, quadrilateral elements, and click OK. And so that turns my model green. I need to then seed the part. The size for these seeds, we'll just go ahead and stick with 2.5. And we're ready to, we need to assign an element type. And if we go to the element type, it automatically chooses shell because we created a shell geometry. We're just going to use linear elements. And here you can see the details of the element formulation, right? So this is a reduced integration using finite membrane strains. And hourglass control and things like that you can specify in here. Basically what this is it's an S4R element, which is a 4-node doubly curved thin or thick shell using reduced integration, hourglass control, and finite membrane strains. So we'll click OK. And now we're ready to mesh the part. So we go up here, we click Mesh Part, and there we have it. Okay, now I think we're ready to run the eigenvalue analysis. So we can go to Jobs. The name of the job, you can give it something that's special to your particular problem. So maybe I'll call this plate eigenvalue. And the source is model 1, so click Continue. And we don't need to do anything with this window, so we'll just click OK. And then we should be ready to submit. And if you want, we can monitor. And the analysis has completed. And let's go ahead and look at the results. So first, you can notice right down here on the screen that it says we're dealing with mode 1. This is the first buckling mode. And the eigenvalue that we get is 9.935. We would take this number and then multiply it by the magnitude of the load that we applied. So remember, I gave the distributed load a magnitude of 1. And so what that means is that the critical load for buckling in mode 1 is 9.9 kips per inch. And if you go back to our hand calculations, you'll see that we had 9.87. So this is actually a pretty good approximation. We can also plot the deformed shape, and you can see that it's buckling in the first mode, so nothing surprising here. We can move to the second mode by just clicking Next up here. This is what the second mode shape looks like, and we also get the eigenvalue for that problem. And then here's the third mode shape as well, but we don't really need that information. I just did that for illustration purposes. Okay, so that's one way to get buckling modes and buckling loads pretty quickly for an elastic buckling problem. We can get the same thing from an incremental iterative analysis, and so in the next step, I will go through and I will do the incremental iterative analysis.
Okay, so the second type of analysis that we're going to do is a static nonlinear analysis. We can go back to the model and where we defined the steps, we're going to get rid of this eigenvalue analysis, so we'll just suppress it. And what I'm going to do is I'm going to create 2 steps. One step, I'm going to apply my imperfection. And this will just be a static general step. And we're going to turn geometric nonlinearities on. We will keep the time period at 1, and we will click OK. The second step will be the step that we're actually going to apply the load. And this also will be a static general step. This is where we apply, maybe I should call this distributed load. We click continue. The time period is also going to be 1 second, but we're going to make some changes to the incrementation because we don't want to apply all of the load in one go. We want to apply increments of the load. And so in order to apply, say, a 10% increment of the load, we're going to change our initial time step to be 0.1 seconds. And for the maximum time step, we're also going to change this to be 0.1 seconds so that we don't apply more than 10% of the load at any given point in time. So we'll click OK. And we don't need to change our boundary conditions because they were applied, in the initial step. So if I double click on boundary conditions, these are still going to be the same and they will carry through the analysis. For the load, because I suppressed the eigenvalue analysis load step, the load also got suppressed. So we're going to have to recreate the loads. Let's do the imperfection first. The imperfection can be applied in a couple of different ways. We can introduce an eccentricity in the load. We can apply a force in the lateral direction somewhere at the mid-height of the plate to force it to bow out of plane. We can also give it an imperfection by giving it an initial out of straightness. The easiest thing to do is to either apply an eccentricity in the load or apply a lateral force here at the mid-height. We'll just apply a force at the mid-height here. The load step, I'm going to give this the name lateral load. And we will apply this in the imperfection step. And these are just going to be concentrated forces that I'm going to apply at the mid-height that would force the plate to have an initial out of straightness equal to L over 100. And so if we do the calculations, that ends up being 4.8 kips total in force. So I'm going to apply a concentrated force. I'm going to apply it at 2 points, here, and I'm holding it on the Shift key. Click Done. And it's going to be a force in the Z direction, and it's going to have a magnitude of half of 4.8 kips, which is 2.4 kips. We'll click OK. And so that's applying that initial out of straightness. And so the way the analysis is going to work is we're going to have a step where we apply these forces, cause it to be initially out of, have some initial out of plane deflection. And then in the second step, we're going to apply a distributed force along the top of the plate that is going to keep increasing in magnitude until the plate buckles. So for our second load, this one we will call distributed load. And this is going to be a shell edge load. And we're going to apply this in step distributed load. And we're going to pick the top edge. And the magnitude for this load, we have to take a guess. So let's pretend that we didn't already go through and calculate the buckling load for this plate. And let's pretend that we didn't already do an eigenvalue analysis. So what we need to do is we need to apply a magnitude that's going to be greater than the buckling load. And there might be some trial and error involved in this. But we know that, let's say if we apply a load of 15 kips per inch, that is going to be greater than the 10 kips per inch that is required to cause it to buckle. So this would be sufficient. Okay, so we're going to apply something bigger than the buckling load. And what's going to happen is the analysis is going to terminate. And even though it's going to terminate with an error, we will still be able to get the results from the model. Okay, so let's go ahead and click OK. And there you have our line load being applied there. Let's double check our mesh. It looks like everything from the previous analysis was saved. So for our element type,
we're still using the S4R element. So we click OK. And we're going to create another job from model 1. And this one we're going to call plate linear. Linear meaning the material is linear, but the geometric nonlinearities are turned on. And it's a static analysis. We click OK. And I like to bring up the monitor box so that you can follow along in your analysis to see like if there are problems converging and whatnot. So basically it'll show you what step you're on, whether it's step 1 or step 2, how many increments you've completed, how many iterations you need for equilibrium, and then what the step time is, the total time and step time are. So this is all useful information for troubleshooting a nonlinear analysis. So I'm going to submit the job. And we're going to follow along in this monitoring box. And you can see that it gives us an error. It says it exited with an error, and it tells us to look at the message file. We're not going to bother doing that because we know why it failed. Basically what happened was, step 1 didn't give us any issues. That's where we applied the 2-point kip forces in the lateral direction. So it's had an initial out of straightness, and then in the second step, we applied the compressive load, and we're applying this in 10% intervals. So we have 0.1, 0.2, 0.3, and so forth. When we get up to about 0.65 or so, then it starts having trouble converging. We have these unsuccessful attempts. So what Abaqus does is it cuts the increment to be something smaller, and it keeps going. And after several unsuccessful attempts, then the analysis terminated. Okay, so if we want to figure out what percentage of the load this would be, we can go to a calculator. Okay, so this is time at failure. And what we're going to do is we're going to subtract 1 second for step 1. And so really we have this being the percentage of the load. And so if I take this and I multiply it by 15 kip per inch, which is the amount of the load, the distributed load that I tried to apply, if I multiply these two together, we get a failure load of 9.84 kips per inch, which is pretty close to the exact solution. We can get some more information out of the model if we go to the results. So even though this says that it aborted and it terminated with an error, we can still go to the results and we can see what happened to the plate up to the point of failure. And so what I'm going to do is I'm going to plot the deflected shape. So this is that initial imperfection of L over 100. And then I can just keep moving through this here, and you can see that the plate eventually buckles. And
That's kind of the end displacement. One thing we might be interested in doing is plotting load as a function of displacement, and so I can get that from my XY data. This is data that's coming from the ODB field output. And what I want is I want unique nodal. And in particular, I want a component of displacement. We could plot the axial displacement, or we could plot the lateral displacement in the plate. Either of those should be give us a similar result. So I'm going to choose the Y displacements, and I'm going to select this node here at the top of the plate, and then I'm going to click plot and dismiss. And what this shows me is a plot of the displacement as a function of time. And what I can do now is I can take this plot and I can convert it into a plot of displacement versus the distributed load that we're applying in compression. And so the way that we do that is we're going to expand our XY data, and we're going to click Edit. And I'm just going to take these X and Y data and copy and paste it into Excel. Scoot this down. So this is time in seconds. This is displacement in inches. And I'm going to basically convert time into compressive load, which will be in kips per inch, by taking time, subtracting out 1 second, and then multiplying it by my distributed load. And then what I can do is I can create my own plot. Where displacement is going to be on the horizontal axis. Hold on, I gotta move this. Okay, so on the x-axis, we will have displacement. And on the y-axis, we will have load. And so you can see that as the load is increasing, displacement is becoming increasingly negative, or it's downwards. This seems like kind of a strange plot, so we might want to actually flip the sign on our displacement values. So that it looks like this. So that was for our linear elastic buckling. Other things we could do is like we could, plot the stresses, and you can see that obviously we're going to have a possibility for the plate to yield here at the middle section. So when we model the problem as material nonlinear, we might get a different result. Okay, so we're going to go through and model the same problem again, except now we're going to turn on the material nonlinear effects. So if we go to Model, we had previously created a section that was plate linear elastic. What I'm going to do is I'm going to create a new section called plate nonlinear. It's still going to be a homogeneous shell. The thickness of the plate is still going to be 1, but what I'm going to do is I'm going to assign the material, the nonlinear material properties for steel. And we're going to click OK. And then up here under section assignments, what I'm going to do is I'm going to suppress the section assignment that I had previously. And I'm going to create a new section assignment, holding in on the Shift key to select both parts. And this is going to be plate nonlinear. And then everything else will keep as the default. And so now what this has done is it's assigned the Ramberg-Osgood material model for steel to the plate. And so now when we apply our load, it could cause yielding as well as buckling in the plate. We can create a new job for this so that we don't overwrite the results of our previous one. And we will call this one plate nonlinear static. And the source will be from model 1. We click OK. And basically what I've done is I haven't changed anything regarding the steps that we have. So we still have the imperfection step followed by the distributed load. For the distributed load, well, for both steps, we have geometric nonlinearities turned on, so that's important. And then the other thing is the incrementation is going to be the same, so we're still going to be applying 10% of the load. And then we can go down here and we can run our analysis. And again, we're going to monitor the analysis while it runs and click Submit. And again, just like in the previous analysis, in step 2, we had the analysis fail to converge. This time, the failure load is going to be something that is less than what we had previously. So let's create Okay, so basically we're just going to copy this stuff down here. And this is our failure load now. It's now at 7.875 kips per inch, whereas before we had something closer to 10. And then the other thing we can do is we can get the load displacement information by looking at the results. Here's the plot of the deflected shape. We can create XY data by selecting the U2 displacement, which is the Y component of displacement. And we're going to select that same node that we had previously. And we'll click Plot and Dismiss. And then we'll take this data. If we click Edit, we can just copy it directly over to our Excel file. And here's our conversion from time to load. And for displacement, we flip the sign, so we're going to do that again. And I'm going to plot this on the same chart. And on the x-axis, we have displacement. And on the y-axis, we have load. And for the series name, we're going to call this material nonlinear. And for the other one, we'll call material linear. Click OK. And so you can see what's happening here is that we kind of have a sharper curve. It doesn't seem to have this increase that we get when we do the linear elastic material properties, because we are getting some yielding that's occurring as the plate's deforming, and so we get a lower failure load. Now, if I were to continue with this analysis, what I might do is I might play around with the time step a little bit and see, like, if I change this from, say, applying it in 10% intervals, if I change it to being 5% intervals, how does that change the result? And I would do the same thing for this analysis here. The other thing I would do is I would not define failure as the point at which the model terminated. So in this case, we said, well, the analysis stopped at 1.65 seconds, so therefore the load was 9.8. That's this point clear out here. We can't compare this point to this point back here because the analysis terminated earlier and we don't know what exactly would happen beyond this. And so I might actually calculate my failure load maybe somewhere around this deformation of 0.4 inches. The other thing I would do is I would look at refining the mesh to see if that changes the result significantly. So I would cut these element sizes in half and see if I get the same result or roughly the same results, or if not, I might continue to convert or to refine the mesh until the solution converges. But basically, that's the basics of doing a linear, elastic, and inelastic analysis of plate buckling in Abaqus.